Hello, this is topic 4.6, half-life. So this is our last topic in this unit. You will need a calculator, so if you don't have your calculator on you, please pause this video and go find it. You do not necessarily need a periodic table today, just calculator. So today we're going to look at, we studied earlier that if the nucleus isn't in that right ratio with protons to neutrons, that it has different means in which it can release radiation, whether it's a particle or in the issue of gamma, a ray, to become more stable. So the next thing we're going to look at is how quickly does that happen depending on the radioactive isotope you're studying. So here we have a graph, and we're basically just interpreting it. So if you take a look at our X and Y, X tells us that this is showing the amount of time in minutes, and Y is showing the amount present. So we start out at time 0, and that means 100% of that radioactive isotope is present, and it shows it going down to approximately 11% after 12 minutes. So you can see that the percent of the radioactive isotope is decreasing with time. So that's one thing we can state about this graph, is that percent of unstable isotope is decreasing with time. And you may recognize this from math. This is showing exponential decay. And another thing we can establish is half-life. So the idea is, like it's showing there, extrapolating there in blue, is that 50% of this isotope remains after 4 minutes. So that tells us that the half-life of this isotope is 4 minutes. So that means only half of the remaining radioactive atoms are there. And so you can look at here, you could go across and find 25 minutes, and about at 7.5 minutes, 25%. So that would be another half-life that it's gone through. So we're going to work on that more with the upcoming slides. So again, like I just stated, half-life is the time that it takes for half of the nuclei to decay. So the amount of time that it takes it's going to vary from each radioactive element. So on this one here, I have an example with the isotope cobalt-60. You start out with 100% or 10 grams of it. After about a minute, 5 grams is remaining, or 50%. So you've decayed half of your isotope. And so, all right, it's gone through one half-life here, and the half-life is 5.27 years. So then half of 5 is 2.5. So it's gone through 2 half-lives, which would put it around 10.5 years. So you can see that it's going to continue to exponentially decay or decrease how much of that radioactive isotope is available. So sometimes it's seconds, minutes, hours, years. And so again, depending on the isotope you're talking about, the amount of time it takes can change. And so when they decay, it's releasing something like alpha, beta, gamma, so on and so forth, in trying to become a stable nuclei. And so again, that's the whole reason why that radiation is being released. So the thing that becomes an issue with nuclear decay is we can't do anything to control it. So however much you have of it, so concentration, the temperature that you store it at, whether you cool it or heat it or keep it at room temperature, or if you exert it under pressure or lower pressure, you cannot change that rate. It has a set half-life, and that becomes an issue with things like Chernobyl. And when you have nuclear reactors using uranium that has millions of years of a half-life, that becomes very problematic. And so this is where a downside of nuclear power can come from. So if we were able to look at a whole sample of atoms, we can't predict when the actual single atom is going to decay, but we can look at the overall sample, and if we know how much of the sample we have, we can predict how much is going to be left. So here we know that the half-life of phosphorus 32 is 14 days. So after 14 days, we are now at half and half of it becoming sulfur 32. After another 14 days, we've now gone through 2 half-lives, so only a quarter of that remains, and then we go another 14 days to 42, and now an eighth of it remains. So again, the overall sample we can study, we can't look at an individual atom and predict to the moment when it's going to decay. So like I said, depending on the sample and material you're working with, it can have a different amount of time it takes to decay, which can be useful. So carbon-14 becomes very useful for archaeologists in looking at if a civilization is found or some kind of artifact is found. We can use that to determine how old it is. Nuclear medicine is becoming very important, especially in the world of cancer. Iodine, for example, has a radioactive isotope that can be used to treat the thyroid. And then we have things like uranium, which is very useful in the geology side of things. We can find rocks, especially in Australia is where a lot of these are found. That's how we're able to date our solar system, and it puts us at about 4.5 times 10 to the ninth years for the half-life. And so like I said, we can use that to determine how old our solar system is. So to give you an idea, Marie Curie is very famous in starting this groundbreaking research in nuclear chemistry. And so this is coming around in the late 19th century. So nuclear chemistry is relatively new in the world of chemistry. We didn't really have a way of detecting radiation until another scientist, Becquerel, came along. And so she kind of took off with him and her husband she met. The Curies did a lot of research. She's one woman that has a Nobel Prize in both physics and chemistry, and so she's the only woman at this time that has 2 Nobel Prizes, and she also has an element named after her on the periodic table. So she did a lot of research, and at the time they didn't really know the health hazards that is nuclear chemistry. And so because of the isotopes she was working with, like polonium, for her, all of her materials that she had in her lab with her journals and that, it wouldn't be until the year 3511 that it goes through enough of a half-life to become stable and safe to handle. So again, that's a drawback to nuclear chemistry. So like I said, carbon-14 is super useful. It has a little bit of a shorter half-life than uranium, and so, but it's still got a long half-life, and so this is where it can become useful in dating artifacts and if we find bones and things like that. And so carbon-14 is radioactive, and we find it in naturally low ratios in the atmosphere. So you can inhale this, and basically you're going to end up exhaling it because, again, you don't use the carbon out of the atmosphere. But what does use the carbon out of the atmosphere are the plants. And so they can use it in the form of CO2. What then can happen is that radioactive carbon in this carbon dioxide can then either be ingested by an animal or yourself. And so that carbon-14 is then used to build up the molecules that makes us. And so the idea is that carbon-14 is constantly being replaced because we are alive and we continue to bring that carbon supply in. As soon as the organism dies, that's when the carbon-14 is no longer being replaced. And so then it starts to decay, and that's where it becomes useful. So like I said, carbon-14 is coming from the atmosphere. It can oxidize with oxygen in the atmosphere to form that CO2. So then plants are what's going to use it in photosynthesis. It's then incorporated into tissues. And so then when this mammoth, for example, dies, the carbon-14 in its bones starts to break down, and we can start to look at the ratio of this carbon-14 to the nitrogen-14 that it has, and that's how we can go along and determine how old these fossils are and other artifacts. So let's get on to the math. Like I said, if you don't have a calculator, please grab one. And so what I have is basically 6 different style problems that can be used to work with Half-Life. So the first thing is I found another teacher made these tables when she was helping her students, and I found them to be very useful. There is more than one way to solve these problems. The big thing is I need to see your work or your thinking. I shouldn't see just an answer. So if you decide moving forward you can come up with a different way to solve, that's fine. You need to show your work. And so what I have for you is what I'm going to call a hat table. So we're going to use H, little subscript L, A, and T. So like I said, the acronym here is HAT, which stands for the half-life, amount, and time. So we're going to make these tables as we go through these problems. So let's look at the problem. So it says if 100 grams of carbon-14 decays until only 25 grams is left after 11,460 years, what is the half-life of carbon-14? So we're trying to figure out how long does it take for half of the atoms to break down. Well, if we take a look, we have a starting amount here and we have an ending amount. So that means at time 0, and before one half-life has occurred, we originally started with 100 grams. So if you think about it, this is going to decay or break down, and each time it goes through a half-life, half of the atoms are going to become stable, the other half remains radioactive. So in our first half-life, we will have 50 grams of our radioactive material decayed, and 50 grams remaining. After our second half-life, 25 grams of the radioactive material will remain, and 75 grams have become stable. So I am done with this part with the amount because I have connected how much I started with and how much did I end with. So we know that at 25 grams, 11,460 years has gone by. So what we can do here is to figure out how much one half-life is. We take our time divided by n, which represents the number of half-lives. So we're going to take 11,460 years divided by 2, and we get an answer of 5,730 years. I am also not going to be particularly nitpicky with sig figs on these. Just again, I don't feel like that's the most important thing to get out of Half-Life right now. So this is how you would calculate if something is asking for the half-life of a sample. So the next one we're asking you to work with is how much total time has gone by. So we're going to make that hat table. And right here it says the half-life of a radioactive sample is 25.89 seconds. So for every half-life, 25.89 seconds must go by. It asks how long will it take 560 grams of a sample to decay to a quarter of its original mass. So what you have to do here is figure out what is 1/4 of 560. Well, a quarter is a fourth. So if you take 560 divided by 4, or take 560 times 0.25, that's 140 grams. So what it's asking is how long does it take to go from 560 grams to 140 grams? So up here at before our first half-life occurs, this is our initial amount, 560 grams before anything's happened. So after one half-life, if we take 560 divided by 2, that is 280 grams. At our second half-life, 280 is going to divide again, and we are left with 140 grams. So that means to go from 560 grams to 140 grams, it goes through 2 half-lives. So this is our initial time here, and so this is before any time has gone by. So at one half-life, so in order for half of this to break down, that is 25.89 seconds. So what happens here is our amount decreases, but our amount of time increases. So in order for this next half-life to happen, we just add these together. So after 25.89 seconds to go on to our second half-life, we add that second amount. So we add that 25.89 and we get an answer of 51.78 seconds. And that is our final answer. So to go from 560 to 140 grams, it took 51.78 seconds. Please make sure that you're labeling your amount in time because, again, these are measurements. So please put units on those numbers. The next style I have is figuring out how old an artifact or sample is. And so we're still using that HAT table, where again, H stands for half-life, A stands for amount, and T stands for time. So it tells us the half-life of carbon-14 is 5,115.2 years. How old is an ancient sample if it started with 16 grams and ended and decayed with 2 grams? Okay, so I know I can connect my two amounts. I know how much I started with, and I know how much is remaining. So we started with 16 grams at my initial time. After one half-life, 8 grams remains. After my second half-life, 4 grams remains. After my third half-life, 2 grams remains. So I've gone from my initial amount to my final amount. So that took 3 half-lives to reduce the number of radioactive isotope atoms. So now we can figure out your time. So again, your initial amount is always considered time 0. In order to go from time 0 to our first half-life, 5,715.2 years must have gone by. So again, your amount will always go down, time will go up. So as your amount decreases, time needs to go by. So to get to our next one, we're going to add these two together. So we're going to take 5,715 and add it to itself. When we do that, we get 11,430.4 years. To move on to our next amount, we aren't doubling this time here. Each half-life is this amount, the 5,000. So each time this is going to increase by 5,715. So we add that on and we get 17,145.6 years. So to get from 16 grams to 2 grams, it must go through 3 half-lives. It increases by the 5,715.2 each time. And this here is my final answer. In the next style problem is you're working backwards to figure out how much of the original radioactive isotope you have. So it tells us the half-life of an isotope is 7,500 or 70,500 years. 13.471 grams is left after this much time. So how much was in the original sample? So we have our HAT table. So the idea is you always want to connect the two units that we have. So in this case, we have years and years. So those two we can work with. In the previous problems, we had grams that we were able to connect. So the idea is we know that we have time 0, and it ended at 2,800 or 82,000 years. And we know for one half-life to go by, we have 70,500 years. So we need to connect these two. So we know for the second half-life to occur, this has to double. 70,500 plus itself is 141,000 years. For our third half-life to occur, it must have another 70,500 years go by. So again, you do not double this. One half-life is the 70,500. So that's what your time will increase by each time. So you get 211,500 years. If you add another 70,500, that gets you to your final time. So we know that in order for this sample to have gone through this many half-lives, it's gone through 4 of them. So the thing you have to understand here is that it says this is how much remains. So this is at the end. So I tell you the amount decreases with time because it's decaying. So now we're working backwards to go back to what it originally began with. So what we're going to do here is we have to actually increase our amount. We know it decays by half each time. So what we're going to do is double these. So we're going to take 13.471 times 2 to give me 26.942 grams. We're going to double that. When we double that, we get 53.884. When we double it again, we get 107.768 grams. And lastly, to get to our original amount, we're going to double one last time, and we get an answer of 215.536 grams. So we wanted to find the original sample. That's at time 0 or before any half-lives have occurred. We're going to now work backwards and figure out how much is left. So in this previous problem, we found how much we started with. In this problem, we're going to figure out how much we end with. So we're going to set up our hat table. So it says gold 198 has a half-life of 2.7 days. How much of this original sample will be left after 8.1 days? So based on my givens, the two things I can connect is time. So we know at 0 half-lives, no days have gone by. After 1 half-life, 2.7 days have gone by. We're going to keep increasing. So we're going to take 2.7 plus 2.7. When we do that, let's see here, let me erase that. So when we add that 2.7, we get 5.4. So for our third half-life, we add another 2.7 to it. When we do that, we get 8.1. That's how I know I'm done, because I've reached how much total time has elapsed. We know that we started at 0 days. We had 96.987 grams of this material. We're going to figure out how much is left, so that means we're going to decrease it. We're going to divide it by 2 each time. So taking that and divide by 2, we get 48.4935 grams. Dividing that in half again, we get 26.24675. Divide in half again, we get 12.123375 grams. So it's asking how much will be left. This is how much that will be left after 3 half-lives have gone by. So H is kind of the same idea, but we're talking about the fractional amount. And so fluorine 21 has a half-life of 5 seconds. What fraction of the original nuclei would remain after 1 minute? So the two things we can connect is the half-life and the total time we have going by. So we can set up our hat table. And this one's going to take up a little bit more space. So we start at time 0, or half-life 0. And so it's every 5 seconds. So we have 5, and we're going to keep going until we get to a minute, or 60 seconds. Okay, so the next thing I can do is start counting how many half-lives we've gone through. So that's 1 half-life, 2, 8, 9, 10, 11, 12. And if you want, you can draw lines going across if that makes your table a little bit easier to read. We'll see how good my spacing was. So we don't have how much we started with. It wants a fraction. So we can assume that at time 0, we have all of our original amount, 100%. As a fraction, we represent that as 1. So after 1 half-life, we'd have half. Continuing on, half of half is a fourth. And we're going to continue to take and divide that in half. I feel like I'm off a line here. Okay, so far so good. So again, I'm just taking half of my fraction. So you can see that very little is going to remain after 1 minute because it's gone through 12 half-lives. So it asks what fraction. So the fraction that would remain is 1,496. If it wanted to know what percent is remaining, you could take 1 divided by 4,096 times by 100 to convert it to a percent. And I don't have that wrote down. But if again it asks for what's the percentage, that gives you 0.0244% is remaining. So like I said, very little because it's gone through 12 half-lives. So this is basically just a run through on kind of the 6 different things that a problem can ask you for. Use this as a guide. If you need more help, if you want me to check something over, please just send me a picture of your work or set up a Google Meet and I will gladly give you a hand. Otherwise, good luck with finding half-life.